good. Let's begin. Let's get our brains warmed up. Do some more of those integral problems that I had last time. Integration quiz on the test, so that'll be a good refresher. A, B, C, D, E. We did E, F. H we did. Okay, F, what are you doing? What do you think? See that? If something like that was on the test, what would you do? Yeah.
You break up cosine 3x to cosine squared x times cosine x times sine x. So
Why?
That you could find one of the trig identities.
I don't. What trig identity are you talking about?
So like I did cosine 2x. Cosine 2x times cosine x times sine x, and then I know cosine squared x is equal to 1 minus sine 2x, and then I did do substitution.
Cosine squared x isn't 1 minus sine. Here, just jump straight into a substitution. Equals cosine. You need the minus sine x dx, which is, it's already right there. So, we'll have a negative on the outside, u cubed du. U to the fourth over 4 plus c. Cosine to the fourth x over 4 negative. Plus c. That's how you do that one. What about this one? So here substitution won't work because if you say u equals sine of x, there's no cosine of x to get that to work. So here, when you don't actually see something that will fix the substitution, here's where you start thinking of try to finagle things a little bit, maybe get a trig identity in there. And we do have a trig identity that can work for the sine squared. The half equivalent or double equivalent, depends on how you look at it. 1 minus cosine 2x all over 2 is sine squared. Cosine squared is 1 plus cosine 2x all over 2. Now, it turns out, integrate 1, you would get x. What is the integral of cosine 2x? Right. You do that by the chain rule. The 2, you multiply by the 2 from the 2x, and that will kill the half. So that's that. Now, technically speaking, even though like no one's ever going to write this out, something like cosine of 2x, technically speaking, you should have done a substitution there. But no one does it because it's kind of easy. So note z something like cosine of 2x the long way. This is set u equals to 2x. Your du would be 2 dx, and so your dx would be 1/2 du, and you can plug this in. And the integral of cosine is the sine of u, so then you have that 1/2 out here, and so that's 1/2 sine of 2x plus c. But you could kind of see, hopefully, that this half would have to be there because if you do the chain rule on this sine 2x, it's going to multiply by that. Another thing is, by the way, cosine squared will be dealt with very similar. 1/2 of 1 plus cosine 2x, so you just integrate that. But this brings up an important point. If your u is linear, only if it's linear. Only if it's linear. If your u is linear, then you can just actually integrate the outer function and divide by the derivative. You cannot do that in general, only if it's linear, because your derivative in this case is going to be a constant. So for example, you can have something that even looks a lot scarier, not even that scary. Let's say you have the integral of sine of 3 minus 2x dx. Notice that if you were to do a substitution, you would substitute this part. That part is linear, which means you can just divide by its derivative. So if you realize that if you divide, the derivative of that is going to be minus 2, you're just going to put a minus 1/2 out here. And just integrate the outer function, which is going to be minus cosine of 3 minus 2x plus c. So that gives you positive 1/2 cosine of 3 minus 2x plus c. So you're not going to really see anyone actually do a substitution for that, because whenever your substitution is linear, it's just kind of easy. Everyone does it in their head. They just divide by the derivative. That does not work in general, only if it's linear. Okay? Because it reverses the chain rule in the constant derivative case. Look at I. What did you guys do here? Yeah.
You would do substitution on arctangent of x. The derivative would be 1 over 1 plus x squared. So your du,
That's what you have right here.
yeah. So
Yes.
your du times parentheses 1 plus x squared equals dx.
And you go and you plug that in. So this is 1 plus x squared to the minus 1 e to the u times 1 plus x squared du.
So the 1 plus x squared cross out. And then you get
So that's just e to the u.
plus c. Oh,
And the integral of that is e to the u plus c. So you just get e to the tan inverse. I saw them put like weird things with arctangent on the finals before, so you need to remember that. You should also remember, by the way, well, I'm going to remind you here, and it was on one of the practice tests. Let's do that. J. Did anyone figure out how to do this one? It's going to be a use of what?
Radical x.
Equals the square root of x. Your du is going to be 1 over 2 radical x dx. So this means that your 2 radical x du is going to be the dx. And you're just going to go and plug this in. So you're going to have 3 over radical x. Now I'm going to leave that radical x because I'm going to want to cancel it with the 2 radical x right here. Now, what would 1 plus x be with this substitution? 1 plus u squared. So notice this, the 3 times the 2, I can factor that out. That's 6 times that guy. And what's this guy? Antiderivative of that.
Arctangent.
That's arctangent. Remember the integral of arctangent. You're going to be doing that for the rest of your life. It's something that people like to ask about. The integral of this and the derivative of arctangent. What about what is it? Yes.
Your u equals tangent of x. I said tangent of x.
So that's just right there. So this just becomes integral of u du. U squared over 2 plus c. So that just becomes tangent squared x over 2 plus c. Yeah, based on what I told you earlier, the integral of sine of 2x is kind of a joke. But integrate the outer function, which is minus cosine of 2x, and divide by the derivative because it is constant. What about this one though? Cosine x times sine of 2x. What did you do here? Yeah?
I feel like you should start with the double angle formula of sine 2x, which is 2 sine x cosine x.
Then what?
And then you could, I think you could, it becomes cosine squared x cosine x. And then you would use up, maybe? You would use up sine x.
Why would you do the sine?
To cancel out the cosine. Or you would also never remember.
Cosine squared.
Yeah, yeah. You would use sub on the cosine x.
Yeah, it's pretty similar to a problem that we had way up the top where it was cosine cubed. We'd use the cosine because that would give us the sine of x. If we use the sine, our du would be the cosine, we'd have an extra cosine left over, and that's not going to be good. Du is minus sine of x dx. So this would just become minus 2 times integral of u squared. U cubed over 3 minus 2 cosine cubed x over 3. So integration we have to be very good with. It's going to be on the test, it's going to be on your final, and in Calc 2, like it's mostly what you're going to be doing, integrating stuff. What I want to talk about now is some applications of integrals. Which I just want to briefly mention some things, not going to go into any detail, because on the one hand, I don't see these things showing up on finals very often, at least as of late, but at the same time, I don't know. They're kind of things that they would expect you to know, just like in general in the Calc 1 class. So I just want to tell you about them, and so just in case we would see them. So one we actually looked at before, and that was with regards to motion. And we looked at the idea that, okay, if you have position, you can move down to velocity, you can move down to acceleration, and to go down in this list, differentiation does it. But to move up in this list, integration does that. Now, I already spoke about that application. We even did an example, so I'm not going to say anything more about that. So that was one important application. Here's another important application, which kind of goes to what we developed integrals to do in the first place, is the area between curves. Saw in the bonus on the review. So I'll just tell you the idea here. Describe it in a picture. So suppose you have one function here, call that f of x, and you have another function below it, call that g of x, and on some interval a, b, you want to actually find the area that's in between these curves. Well, what you can do is find the area below each individual. So, what we can do is something like find the area under the f of x, and that's going to be the green here. And then you can find the area under the g of x. And that would be the area here. And just notice to find the area in between, what you would do is you just subtract them, right? So if I can find this area under here, and then that area under there, the area in between is just the big area minus the small area. So a negative sign will come in front of here. But because of how integrals work, we know they distribute across sums. We can kind of write everything under one big integral, which kind of gives us this idea here, which is going to be important. A lot of times it's nicer to think of it in terms of position, or how things relate to each other, position. And so it's probably nice for you to think of area as the integral of the top curve minus the bottom curve. That gives you the area between two curves, x. Now, you're pretty much never going to be asked this, I don't think, but you should know that you could turn the situation around. So sometimes you might have a function that is best described as a function of y because it doesn't pass the vertical line test. So you might call this something like g of y. And there's another function that's like here, but in terms of y, f of y. And you might want to measure the area between these curves, some distance on the y-axis, like between C and D. You might want to find this area here. So it's kind of like you tilt your head to the side and you kind of do this situation. And for the dy situation, where you're looking at things as functions of y and your limits are coming from the y-axis, then your area is going to be right minus left. If you're thinking of things in terms of y's. And in Calc 2, you're going to start to be able to switch between these two. In Calc 3, it really starts getting crazy. But yeah, there's nothing that says we have to be stuck on the x, and the x-axis is what we have to dissect. We can dissect the y-axis. And you're going to be doing that in Calc 2, and you're going to realize that we can just make up a curve that we want to integrate along and dissect that, and that's going to be in Calc 3. So, yeah, area is just top minus bottom, or right minus left, depending on how you want to look at it. And sometimes the area so we're never really going to give you a question at this point where they switch roles, so let's not talk about that and confuse anybody at this point. But what you should be aware of sometimes the limits on the integral. So sometimes you're not going to be given A and B. We're just going to tell you about two functions, and we're going to say something like, find the area bounded between the two functions. And basically what you're going to do is you're going to figure out where these two functions intersect. So, i.e., you want to find the area bounded between two functions. But the interval a, b, not unit. So sometimes what will happen is you'll have two curves doing their thing, and the intersection points would define the points that you integrate between. And that can define your a and b. This is say p of x, and this is m of x. In this case, the formula for area would be, what would we integrate? Yeah?
f of x minus p of x. Well, yeah.
Use x mixes.
It's top minus bottom. Who's on top?
Oh, p of x, oh, yeah, yeah.
It's always top minus bottom. dx. So you saw a question like this in the bonus. Basically, that's what I did. It said, find the area bound between two curves. I just set them equal to each other to find the intersection points. And then I figured out who's on top, who's on bottom. And then I integrated the subtraction in the correct order. And that will give you the area between the curves. Another important application is something called the average value. You also saw this in a couple of the bonuses on the review. So this is like when you have a function doing its thing again, and you're on some interval a, b, and notice that you can find coordinates, points along this function. And so you can get a bunch of y values here. Let's call this guy f of x. And now the question would be, what is the average y value? So, average in the sense of the mean average. So what you can realize here is if we select n points, then the mean is going to be, well, f of x1 plus f of x2 plus f of xn all over n. But we can notice that if we look at how these guys are separated, remember that delta x is b minus a over n, therefore n would be b minus a over delta x, using a previous formula, which means I will be able to flip this, keep, change, flip. And then delta x comes on top and multiplies everybody. And you'll notice what we have here is I can actually write this as a summation. But that's just me selecting n points. To select all the points, you simply take the limit as n occurs to infinity. To say I'm going to select an infinite number of points here so that I can get all of them. And of course what you end up with is the integral from a to b of f of x dx by definition, and you'd end up dividing by 1 over b minus a. And so we can use integration to find the average value of some function that it's not even separated by values that we can count. If f is integrable, its average value. 1 over b minus a times the integral from a to b of f of x dx. I'll tell you the average output of your function on some interval. Which might be important from time to time. So that's a very important formula, even though lately I don't see them, they used to ask about this all the time, but as some of you might know, we have a new syllabus now, and so you don't really see these that often anymore. So some of these little computational applications, they drop them out to make way for these more proofs and things like that, because they want you guys to be able to actually read arguments and do mini proofs. So they don't really do this much anymore, but hey, just in case. So it says, what's the average value of f on this interval? Just do that formula. That's going to be the formula. So I memorize these applications last, right? If you're studying, you feel like you got everything, study these just in case. Probably not too likely it will show up, but there's a small chance it will show up. There's also something called the mean value theorem for integrals. So we saw the mean value theorem for derivatives that says on some interval, there is a point where the instantaneous rate of change is equal to the average rate of change on the interval. We can talk about the average value of a function on the interval as well, and we call this the mean value theorem for integration. So if f is continuous on a b and integrable then you kind of assume the variable here, but then there is C. Such that the output of this function at C is going to be equal to the average value. X squared. Find the average output on 0, 1. At what value in 0, 1 does f attain its average value? And you can use these little theorems to prove a lot of other nice things. But, yeah, here, we know that the average value is given by 1 over b minus a times the integral from a to b of our function x. Here, b is 1, a is 0. 1 over 1 minus 0 times the integral from 0 to 1 of x squared dx. And this is going to be, well, that's just 1. X cubed over 3 from 0 to 1, so that's a third. Which means if you're looking at this function, y equals x squared on 0 to 1, and you're focusing on all these outputs of all these y values. If you take all these x values here, compute all their squares, and then you could add them up and divide by the number of things there are. If you could do that, you can't do that in reality because you have an infinite number of things to add up. The answer would be a third. On average, y equals x squared outputs the value of a third. And so in part 2, we just want to set f of c equals to a third. This means that c squared would equals to a third, which means that c is going to be plus or minus 1 over radical 3, which means you take the positive. C equals positive 1 over radical 3. That is a number smaller than 1, so there's going to be that number here, say 1 over radical 3, and at that input, the output is going to be a third, which is the average value. We know that the maximum value is 1, the minimum value is 0, but on average, the output is a third. And there's a point in that interval that actually gives me the output of the third. And again, this in and of itself doesn't seem that impressive, but look at what we could have done with the mean value theorem. We literally found the fundamental theorem of calculus with the mean value theorem as help. So this guy can actually help you do a lot of interesting things. We do a lot more applications in Calc 2. This is just some honorable mentions that we don't really do anymore, but I don't know. I have no control over what they're going to write for the finals. We haven't been in this new syllabus for too long, so I can't. My powers of prediction aren't that great, so I just decided, hey, let me just kind of say this just in case. And if you have time to look over this, do. But yeah, that's basically it. So we can use integrals to do problems with motion, which you should know how to do. I think that's going to be, things like that could come on your final. Finding error between curves, very common thing to ask about. Finding average value, as well as dealing with the mean value theorem for error. When you go to Calc 2, you'll do a lot more application of integration. But for now, I think that's where we want to end. That's it. That's all I wanted to say for Calc 1. And now let's have a really decent farewell. So you guys are ready. And I think everyone is here.